Hello everyone, my name is Harun Mahdirate. I'm Professor of Chemical Engineering at University College London, and today I'm going to talk about combating global warming. Is CCS the magic bullet? So before I start, I'm going to show you a video about the global warming, what the issues are, and we start now.
You can't see it, you can't smell it, but it's actually all around us, and it's at the heart of our climate crisis. CO2 is a gas made up of three parts, or atoms, one carbon and two oxygen. Its full name, carbon dioxide. It occurs naturally in our atmosphere, and it's a vital part of life on Earth. People and most animals breathe in oxygen and breathe out carbon dioxide. Plants use CO2 to help them grow. But it has a much bigger role to play too. It helps regulate the temperature of our planet. That's because CO2 is one of the main greenhouse gases. It acts like the glass in a greenhouse by keeping some of the heat from the sun trapped inside the Earth's atmosphere. That's a good thing because without it, the planet would be too cold for us to live on. But the natural world works on an incredibly delicate balance, and human activity, especially over the last 50 years, has increased the amount of CO2 in the atmosphere. Too much of the sun's heat is getting trapped, and our planet is getting hotter. So where's all this extra CO2 coming from? In short, it's from modern life. Factories, cars, aeroplanes, large-scale agriculture. They all use what we call fossil fuels: oil, coal, and gas. Now, over hundreds of millions of years, the remains of plants and animals, which are full of carbon, have been buried under the surface of the Earth. Some fossils eventually turn into fossil fuels. So when we burn them, all the carbon which has been stored up over an incredibly long period of time gets released really quickly as CO2. It's still only a tiny percentage of all the air around us, though, just over 0.04%. Scientists measured that as the number of CO2 parts per million in the air. In January 2020, it was an average of 413.4 parts per million. But in 1970, that number was 325, and at the start of the industrial age, it was roughly 280. The increase has been huge, and CO2 levels have been accelerating fast. They do fluctuate naturally, but they haven't been as high as this since well before modern humans like us even existed. In fact, experts reckon the last time there was this much CO2 in the atmosphere was probably more than 3 million years ago, when sea levels were 15 to 25 meters higher. So, in order to sustain life on Earth as we know it, we do need to limit the amount of CO2 that gets released. And that's why the climate change debate has become so urgent.
Okay, so you've seen the issue, carbon dioxide. If there's too much of it in the environment, it causes huge problems, global warming. So why should we be concerned? First, the effects of global warming: biodiversity loss, sea level rise, wildfires, water shortages, crop failure, extreme weather. We look at some of the consequences. Millions displaced can result in disease, increased risk of wars and conflicts, and impact on human rights. So where does all this CO2 come from? Here is a diagram which shows the contribution from different sources to the overall CO2 emissions into the atmosphere. As we can see, we have several contributions from different sectors. The largest one is electricity production. When you generate electricity, you need fuel. When you combust that fuel, you generate CO2. So electricity is one of the major contributors for CO2 generation. Other fuels consumption, such as for transport, contribute to about 10%. Land use change and forestry, 24%. Transport, we can split it into aviation, which is 2%, that's airplanes contributing to the CO2 global emissions. Other modes of transport, 16%, and industry, also a very large contributor to CO2 emissions. Is steel industry, for example, cement, refineries. They all use energy. That energy comes in the form of burning fossil fuels. And of course, if you burn fossil fuels, then you produce CO2. So Why is it urgent? Why do we need to do something about it now? Well, this is a very interesting, very useful diagram which shows the extent of the problem in the context of the change in the global average temperature. So what we have here is a simple plot which shows the total emissions of CO2 from all the different sources that we talked about, expressed in gigatons, that's billions of tons of CO2 released per year, and how that amount of CO2 changes on every decade. So starting from 2000 up to 2100. And we have three curves here. The blue curve that I'm showing here is if we did nothing basically about CO2 emissions. That is, we left things as they stand, and we could see that by 2020 we start shooting off in terms of the CO2 emissions, huge amount of CO2 emissions. As we continue this path, we would end up with a temperature which would be approximately 4.5 degrees C above the average pre-industrial levels. That would be disastrous, and we wouldn't be be around to see that temperature. In fact, if by around 2030 or so, it would be a point of no return. That would mean that whatever we did beyond that point, it would be basically too late. This is the orange curve here, on the other hand, shows the situation as things stand, following a lot of effort in order to reduce CO2 emissions. So as we can, let's follow the path of this curve. Basically, as we see, obviously, there is the amount of CO2 which is being released into the atmosphere is far less because of the actions that we've taken. And if we follow this path as things stand, we would hit a temperature which would be 3.5 degrees C above pre-industrial levels. That is, again, catastrophic. In fact, by around 2050 or so, it would be the point of no return. Once again, that would mean that whatever we did beyond that point would be basically too late. Now, if we take drastic action, wake up to the challenge, and deal with the problem, this is the scenario that we would like to follow. And as you can see, that would require a drastic, continuous reduction in the amount of CO2 which is being released. And if we follow this path, we could reach net zero. That is, total amount of CO2 which is released into the atmosphere would be around zero. And by then, the average temperature would be about 1.8 degrees C above pre-industrial levels. So what can we do about it? How can we follow the green line that I just showed you? Well, first came the Paris Climate Agreement, and the internationally agreed climate agreement reached by 195 nations at the Paris Climate Conference in 2015 is intended to limit the increase in global average temperatures to well below 2 degrees C above pre-industrial levels. Let's explain what we mean by 2 degrees C above pre-industrial levels. So by that, we mean that if we go back, for example, about 100 years ago, before the advent of electricity, in heavy industry, the average temperature, if by then was around, let's say, 15 degrees C, we want to not exceed that temperature by not more than 2 degrees C. So 17 degrees C would be the maximum that we would want to reach. That is the absolute maximum, and what we need to do is go well below that. Bearing that in mind, this was superseded by the European Union, and the net zero emissions target was defined. That is that the net amount of CO2 released into the atmosphere would be zero by 2050 in order to avoid irreversible climate change. So we move on. So how big is the challenge? How much CO2 we need to remove to reach this net zero emission target? So let's make sure we understand what we mean by net zero CO2 emission target. Basically, what it means is that the total amount of CO2 which is released following drastic reductions any remaining in CO2 which is released into the atmosphere is balanced out by removing it from the atmosphere through different various means. So if we plot, again, same kind of figure that I showed you before, this is the total amount of CO2 which is released into the atmosphere as a function of years, plotted starting from approximately 1970 up to 2100. The gray curve shows the situation, the path that we've been following since. We are at the moment releasing approximately 45 billions of tons of CO2 per year. If we were to follow the net zero target, by 2050, we would need to follow this path. That is, that we would need to remove approximately 45 billion tons of CO2 from the atmosphere per year. And if we have a more ambitious target of hitting the net zero target by 2040, this is the path that we would need to follow. So, where does carbon capture and storage, or the abbreviation CCS, comes in? Is it the magic bullet? Now, let's explain what we mean by carbon capture and storage. Basically, CCS is the process of capturing and storing CO2 before it is released into the atmosphere. The technology can capture up to 90% of the CO2 released by burning fossil fuels in electricity generation and industrial processes such as cement and steel production. So as you can see, it has a major role to play. To capture 90% of the total CO2 emissions is really indeed a big deal. And if that can be done through the application of CCS, then that goes a long way in addressing global warming. In fact, without CCS, many people believe that it will be near impossible to reach the CO2 emission reduction targets fast enough to avoid irreversible environmental catastrophe. Just to make sure that we understand the concept, I'm going to show you a video which explains the whole idea about CCS. So,
for CCS to deliver on its promise of reducing CO2 emissions, they must be safely and permanently stored underground. By injecting CO2 underground, we are in effect returning carbon back to where it came from. We extract carbon as coal, gas and oil, which are burnt to produce energy. The resulting CO2 emissions from power plants and heavy industry can be captured before being pumped underground, closing the carbon loop. How do we store CO2 safely and permanently underground? By imitating trapping methods used by nature to store CO2, gas and oil for millions of years. And by using existing technology to transport and inject the CO2. Technology which has been used for decades by the oil industry. Storage starts by pumping liquid CO2 into a carefully chosen reservoir. There are two main types of CO2 storage reservoirs: deep saline aquifers, which contain undrinkable salt water, and depleted oil and gas fields, both of which have the same key geological features to safely store CO2. A suitable CO2 storage reservoir needs a layer of porous rock at the correct depth to hold the CO2, sufficient capacity, and an impermeable layer of cap rock to seal the porous layer underneath. Once the CO2 is trapped under the cap rock, three additional mechanisms, residual, dissolution, and mineral trapping, ensure that the safety of CO2 storage sites actually increases over time. How do these mechanisms work? Some of the CO2 injected into the smaller pores simply cannot move, even under pressure. This is residual trapping. A portion of the CO2 dissolves into the salt water. This is called dissolution trapping. The CO2-rich water is heavier than the surrounding liquids and migrates downwards, where it may react to form minerals such as those found in limestone. This is mineral trapping. To ensure that a CO2 storage site functions as it should, a rigorous monitoring process begins at the reservoir selection stage and continues for as long as required. The well, caprock and adjacent rock formations are monitored for changes in pressure and CO2 concentration levels. All of these systems ensure that response times are swift and decisive action can be taken when necessary. Monitoring continues even after a well is closed, and EU law requires that stored CO2 is kept safely and permanently underground. How much storage space do we have? Large potential CO2 storage sites exist all over the world. Europe alone can store 60 years of current annual CO2 emissions from power plants and heavy industry. So with careful site selection and monitoring, the safety of a CO2 storage reservoir increases over time. Time we will need to switch over to the sustainable energy systems of the future. ZEP, the EU's authority on CCS.
Right. I hope that gave you a clearer picture of carbon capture and storage. And so what are the challenges to make CCS a success? But there are several. First is reducing the cost. Capturing the carbon dioxide, which would be otherwise emitted into the environment, requires energy. And that increases electricity bills. Transporting it to storage requires the construction of long pipelines. Next is improving the safety. Although harmless under atmospheric conditions, CO2 at high concentrations, let's say around 10% volume per volume, is an asphyxiant. Next is also we need society on our side. We need to have public acceptability. Public support is essential for CCS to be successful. So we've got some work to do. Over the past decade, UCL Chemical Engineering has been at the forefront of CCS research, addressing the above issues. This has been through leading international collaborations across 10 countries in Europe, Canada, China, and the USA. Here are some of the projects that we led at University College London to address those issues, funded by the European Commission through two programs, the Framework 7 and also the EU Horizon 2020 projects. These involve multinational collaborations with partners across the world. The first project, CO2 Pipe, has 2010 to 2013 focused on the safety issues associated with the transportation of CO2 using high pressure pipelines. The next project, CO2 Quest, focused on the cost associated with the purification of the CO2 before it can be transported using pipelines for permanent storage. And our next project, the current one, 2020 to 2024, which just started, looks at developing capture technologies for capturing CO2 from the steel industry. So I'm going to show you some of the partners which have been involved in the various projects that we have led at UCL. As you can see, there are many from many different countries, around 9 countries in Europe, including China and the USA. I'm going to go through a brief description of what we did during the course of the CO2 Pipe HAZ project, which involved looking at the safety issues associated with the transportation of CO2 using high pressure pipelines. In CCS, pressurized pipelines are the most practical method for transportation of CO2, which is captured for permanent geological storage. But as I said before, the problem is that CO2 is an asphyxiant, and it is likely to be fatal at concentrations greater than 10% volume per volume. So in the unlikely event that these pipelines rupture, we need to understand the consequences. And if we understand the consequences, then we can plan to deal with them. So the safe operation of these pipelines is fundamentally important. And the questions are, important questions are during the CO2 transportation of CO2 using pipelines is the dispersion behavior of the released CO2 cloud. in the unlikely event of pipeline failure, how far will this CO2 plume travel? What is going to be the concentration of this CO2 cloud? When we started this project, nobody had the answers. In fact, there were no experiments conducted which actually mimicked this sort of scenario relating to a pipeline rupture. And the next question that we needed answering was, well, CO2 transportation, we've been transporting hydrocarbons using high pressure pipelines for decades. CO2 transportation is relatively new. It has been transported before, but not at large scale, and certainly away from populated areas. The question is, do we need special pipeline materials when we are dealing with the transportation of CO2? As I said, one problem is if we have small amounts of water, CO2 combines with water to form carbonic acid, and carbonic acid can cause corrosion. Next question is fracture toughness. Do we need special types of materials in order to resist running fractures when we deal with transportation of CO2, given its very different physical and thermophysical properties as compared to hydrocarbons? So these were some of the main questions that we wanted to answer during the course of the CO2 pipe hazard project. So we applied for funding to the European Commission and we were successful. I led a team of scientists across 6 European countries in collaboration with China. And the role of our Chinese partners was pivotal. Basically, their role was to construct a pipeline that could mimic a real situation for transporting CO2 under high pressure. And we had to basically rupture that pipeline safely and look at the different consequences. Here is our team in China. I briefly introduce them. We have Professor Zheng on the left here, Dr. Chen, and Professor Yu, and I'm here myself, Harun. And we started this project approximately 8 years ago. We found some land well away from populated areas, and we went about constructing our pipeline. And here we had to clear the land, and we came across wildlife. This is an example of a snake which had to be caught and housed safely and released back into the environment later on. And this is a pipeline that we built in China. A diagram of it, 250 meters long, the first one ever built in the world at such length, instrumented so that we could understand what goes on inside the pipeline, pressurized, and we were able to measure the pressure and the temperature of the CO2 contained in the pipeline at any point along the length of the pipeline. We had the diaphragm at one end here. We ruptured the pipeline and we took some measurements of the changes in the pressure and the temperature along the length of the pipeline. And we also measured the concentration of the CO2 cloud, which was released. These are 2 photographs of the pipeline here. One is the pipeline, this one on the left is the pipeline, one end of the pipeline, and this is the other end of the pipeline, the release end of the pipeline. You can see here is a hole, basically behind it is a diaphragm. Once the pipeline is pressurized, whenever we wanted to do a release experiment, this diaphragm was ruptured and we started taking our measurements. Give you a better appreciation of the scale of the problem. Pressurizing carbon dioxide to 70 bar pressure at such large amounts, we would typically had to load the pipeline with approximately 10 tons of CO2 at 70 bar pressure. And to rupture the pipeline, the amount of energy which is released is absolutely enormous. We are talking about a few kilograms of TNT. So part of the engineering design involved making sure that following the rupture of the pipeline, the pipeline didn't take off. The amount of energy which is released following a rupture is equivalent to firing several cannons. So we had to take special precautions and provisions by making sure that the pipeline is well anchored so that it wouldn't take off. This is to give you, again, a perception of an appreciation of the scale of the pipeline itself. We had to make the pipeline large so that the experiments that we conducted were as close as possible to what would happen in practice. I'm going to show you a video of one of the experiments that we conducted in China, an aerial view. This is the pipeline which we built in China, pressurized, and I'm going to show you this is the video of a typical, one of the many experiments that we conducted in China. Pipeline is pressurized, and then we triggered the rupture disk, which as you can see, the effect is on the land itself. The area is absolutely tremendous. During this experiment, we were able not only to measure the mass releases rate of the CO2, which was being released from the rupture point, we also measured the concentration of the CO2 cloud as the CO2 was being released at different locations by having probes located, concentration probes located at different points, and measuring the concentration of the CO2, with in particular trying to find out if ever the concentration of the CO2 reached a dangerous level, that is above 10% volume per volume. Of course, we found, as we would expect, close to the proximity of the rupture plane itself, the concentration, of course, did reach significantly more than 10% volume per volume, which is the dangerous level. But as we moved along away from the point of release, the concentration of the CO2 decreased rapidly. So this experiment provided us with enormously useful data for us to be able to understand what's the safe distance from a CO2 pipeline in the event of an accidental rupture. So the idea is that if we were to build this pipeline near a populated area, what should be the minimum distance of people who would be able to live close to this pipeline in the unlikely event of an accident? Data which was never available before, and this is the first time that we were able to record and report that data. Another question is basically brittle fracture propagation. Very interesting problem. Carbon dioxide, when it expands, it cools down. If you, for example, you have carbon dioxide at a pressure of 70 bar, which is the type of pressure that we would be transporting carbon dioxide, and you're transporting, imagine a situation that you're transporting this CO2 in a pipeline, and there is an accidental pipeline puncture due to, for example, a corrosion of the pipeline, or a mechanical digger accidentally collides and punctures the pipeline. It goes unnoticed. Carbon dioxide is released slowly. As the carbon dioxide under high pressure is released, it expands. And as the gas expands, it cools down. And our experiments show that the temperature of the carbon dioxide can reach minus 70 degrees C once it's released from 70 bar pressure. So the question is, how will the pipeline material react at low temperatures? Will it still be able to withstand the pressure, or is it going to fracture? Very important question. And again, nobody knew the answer at the time. So to give you an example of how a typical material behaves under room conditions, room temperature, for example, under stress. So you can see this is a typical material steel under at room temperature, under stress. As you can see, it plastically deforms, so it slowly ruptures, fractures. However, if we drop the temperature to, let's say, minus 65 degrees C, same material, same experiment, we apply stress and see how the material behaves. Minus 70 degrees C, as you can see, immediately you get a running fracture, brittle fracture. And if that happens in practice with a CO2 pipeline, you can have a running fracture, instantaneous running fracture. So a small hole can transform potentially in a brittle running fracture, resulting in a significant amount of CO2. So this is a big question mark that we need to answer. We have initial puncture. Can we have a scenario that after a time the pipeline gets so cold that the initial puncture results in a rapidly running fracture, followed by the splitting of the pipeline and the huge amount of CO2? Obviously, that's something that needs to be avoided. Again, nobody knew the answer then. So in France, our partners at INRIS in France were able to mimic this sort of situation. So what we did in those experiments, we took a pipeline, a section of the pipeline, pressurized it with CO2, and we had a series of thermocouples placed at different locations from a simulated puncture. Pressurize the CO2, puncture the pipeline, and measure the temperature of the wall of the pipeline and see what sort of temperatures we would reach in those sort of scenario, as close as we would get in a real situation where puncture would occur. And due to those experiments, what we were able to look at the local temperatures in the vicinity of the pipeline. And this is basically an infrared recording of a puncture experiment. The blue area here shows the minimum temperatures. And as we move along the temperature, as we remove into the red and into the yellow zone, the temperature increases. So if we are in the blue region, we are looking at temperatures of around minus 10 degrees C. If we are in the yellow region, which is around here, or the orange region, we are around the temperature of 7 degrees C. So as you can see in this experiment, the metal temperature, or the ambient temperature, not the metal temperature itself, as you can see in here, reaches around minus 10 degrees C. The metal temperature goes below that. If we have this scenario for a buried pipeline where the gas can escape at that so freely, it would be in contact with the pipeline itself. So in the case of a buried pipeline, the situation could be even worse. So the pipeline temperature could hit much lower temperatures than we are seeing here. So our next experiment that we intend to do is basically looking at a scenario where the pipeline punctures and it's buried, and see what sort of temperatures we would encounter, and if those temperatures are low enough, which would be resulting in a brittle fracture of the pipeline and ultimately a running fracture. So here I stop and I move on to my next slide. Another experiment. We are scientists. We were very interested to find out what goes on inside the pipeline when the CO2 is being released. Very important to know, is the CO2 which is being released, is it going to liquefy as a result of a reduction in the temperature? If it liquefies, are we going to have two-phase flow? Very important questions when you want to do mathematical modeling in order to predict the release rate of the CO2. So for the first time ever, our colleagues in France were able to construct a pipeline with reinforced glass along its length, and we were able to see what goes on inside the pipeline during a release experiment. And here is a video of what we did. So here is the release has very clear. They have basic initially followed by that mathematical modeling in order to predict the release rate. It's very important to understand the different flow regimes for the modeling of the release process. So here I stop here. I think I've run out of time. I hope I've given you a better understanding of the impacts of global warming and the major roles that CCS has to play, along with some of the work that we've been doing at University College London in order to promote CCS, in order to basically reduce the costs associated with it and improve its safety so that it becomes as an important tool in our fight against global warming. Thank you for listening. Time for some questions. I've seen quite a few posted here. The first one, what is the cost of CCS systems? Well, as I explained, the main costs are associated with the capture process. If you capture CO2, require energy, and energy costs money. The second important element is the pipeline transportation of CO2. To transport the CO2, you need to construct very long pipelines. Typically, these can be several hundred kilometers long, and they have to operate at high pressures, and therefore there is a large cost associated with them. Second question, how about transportation of CO2 using plastic pipelines to avoid fracture? Excellent question. Well, there are two main issues associated with this. The first is that it's not possible to make plastic pipelines which are strong enough to transport such large volumes of CO2 at such high pressures. And also the second problem is that some contaminants in the CO2, even if present in small proportions, may react with any plastic materials, which could cause leakage. Next question, can we stop corrosion using ceramic lining? Very good point. Well, it would be very difficult to line pipelines with ceramic. You can use polymers to line pipelines which resist corrosion. However, the problem is again cost, and also corrosion is a major potential issue that we really need to avoid during CO2 pipeline transportation. The problem is that even if you have small amounts of water, it can easily react with the CO2 to form carbonic acid. And carbonic acid is highly corrosive, and it could attack the pipeline material and cause corrosion. So the way forward is to make sure that the CO2 which is transported is as dry as possible, with very small parts per million at the most, so as to avoid the risk of corrosion altogether. Next question is, has CO2 been let me read this. I think I skipped one. Oh, other than CO2, what are the remaining greenhouse gases? Well, methane is a major greenhouse gas. In fact, its impact on global warming is 10 times as much as CO2, weight for weight. But the problem is that the amount of CO2 which is released into the atmosphere is orders thousands of times more than the amount of methane which is released. So if we need to do something, CO2 is the first that we need to deal with to reduce the global warming effects. Next question. CO2 has been transported using pipelines in the US. What are the issues? Excellent question. Yes, indeed, it is true. CO2 has been transported in the US using pipelines. The problem two problems. First is that the CO2 has been transported mostly in very pure form, so there aren't any contaminants. And what we've established during our work during the FP7 project that I talked about, if you have small quantities of impurities, these will have a major impact on the pipeline material of construction that you need. Also, the other problem is that these pipelines are very much away from populated areas in the US. They are used for enhanced oil recovery mainly, and also for use of CO2 for fizzy drinks, for instance. So the issue is that the fact that they are away from populated areas, so we have very little information about the risks and safety associated with these. In the context of CCS, the problem is that CCS, these pipelines will inevitably pass through populated areas. So the risk that we can tolerate is going to be far less than what they would be in the US, where we have pipelines away from populated areas, where the risk of rupture is not that significant as they would be if this happened near a populated area. So we really need to take extra precautions, and there is a huge amount of additional understanding that we need to gain before we can confidently transport CO2 in pipelines. For CCS, I'm not saying that it's impossible. In fact, it's all very doable, highly practical. The thing is that the best way to approach it and what's the most cost-effective way and the safest way of doing it. Next question, how successful were the experiments in China? What were the challenges? Well, thank you for asking this. The experiments in China were really successful thanks to our colleagues in China. Extremely competent engineers. To do the kind of tests that we did is extremely challenging. You're looking at constructing a pipeline, which is very long, operating at a high pressure of about 70 bar, instrumented, and that means inserting thermocouples and pressure transducers into the pipeline and making sure that they are sealed at the same time, so there is no leakage. And this to be followed by rupturing the pipeline in a safe manner. This is incredibly challenging, and we did encounter several problems. Of course, we weren't successful first time. Again, thanks to our Chinese colleagues, we overcame the problems through their significant efforts, and we were able to conduct the tests and produce for the first time very comprehensive set of data as to exactly what can happen as far as the dispersion of a released cloud is concerned following the accidental or unlikely rupture of a CO2 pipeline. What are the safety distances? And some of the measurements that we took are incredibly useful for modelers, mathematical modelers, to produce mathematical models in order to predict the discharge rate from pressurized pipelines in the event of an accidental rupture. Next question, the last one, impact of COVID-19 on the environment. Let me think. Yes, indeed, very good point. As you heard through the media, the less use of traffic, industry not being active, have all made significant contributions to the amount of CO2 which has been monitored. There has been significant improvements, in fact, as have been reported, and it just goes to show what can be done by humanity in order to reduce CO2 emissions through their day-to-day lives and also activities. But the problem is that we cannot stop industry. We can't stop using public transport. We can't stop driving our cars. What we can do is, of course, try and develop technologies where the CO2 is emitted up to a minimum amount, and also capturing the CO2, which would be otherwise emitted in the environment. And this is where carbon capture and sequestration plays a major role in capturing the huge amount of CO2, which would be otherwise released in the environment, and help meet our ambitious targets in achieving net zero emissions by 2040 or 2050. I can't see any more questions. And again, thank you very much for your attention. And I hope you enjoyed this presentation. My contact details on the first slide. Please help yourselves if you wish to contact me. Email is there. I'd be more than happy to answer good questions. Take care. Bye.